Good morning, everybody. I welcome you all to this webinar. This webinar is called Faster Queries, Lower Bills, and Smarter Databricks Ecosystem. I would like to first thank you all for tuning in. The webinar, as the name suggests, would cover the aspects of cost, optimization, and performance tuning of your Databricks workflows. So over the next hour, we'll show how leading companies who we are working with are shaving tens of thousands of dollars off their Databricks invoices while actually speeding up their pipelines. And by the end of this webinar, you'll know the exact levers to pull, what parameters to tune, and uh, what to optimize. So just to ground today's discussion in a bit of credibility, here's the Royal Cyber snapshot. We have about 20 years in the game, which means that we've seen every wave from like an on-prem BI to today's Gen AI, and we've learned how to productionize each one from on-prem to Gen AI, on-prem BI to Gen AI. We're more than 2,000 specialists, including 500 plus certified consultants across multi-cloud, AWS, Databricks, Snowflake, SAP, Salesforce, etc. And that breadth alone, it gives us the ability to stitch solutions end to end instead of handing you a pile of siloed tools, right? Our 10 plus offices in 5 about 5 continents support a true follow the sun model. So like issues raised in Chicago at 5 p.m. are already being worked on uh, across the world. So we've delivered value for over 600 plus clients, retailers, banks, telecoms, pharma, you name it, all of whom pushed us to optimize for both cost and performance. And finally, the partner row at the bottom, you can see that we have AWS, Microsoft, Oracle, Databricks, SAP, Snowflake, and this means that whatever stack you choose, whatever stack it may be, we're already vetted and integrated in that thing. So before we jump into the nuts and bolts, a quick hello from us. My name is Haider Jan. I'm a data and AI engineer at the data analytics department, and I'll be covering the optimization playbook in the first half of this webinar. And besides me, we have Maz Ahmed, who is a data scientist, also is in the data analytics department at Royal Cyber, and he'll be showcasing a live case study and a short demo. He'll be providing the techniques we discussed. We'll be discussing in the first half, and we'll be just discussing the techniques that actually work in the real world. So between us, we cover the full spectrum from cluster level cost engineering to model level intelligence. So feel free to aim your questions at either one of us during the Q&A. Right. So here's a roadmap for the next hour, so that you know exactly where we are headed and why each point or each step matters. In step one, we'll be going through the introduction, in which we give you a quick context on what the Lakehouse platform is and how it serves as the ground truth for data. At step two, we'll be talking about the data analytics and Databricks. So a fast tour of a Lakehouse stack from data engineering to Gen AI, right? In step three, which is the cost problem, we'll quantify how quickly DBUs add up and where the hidden drains lurk inside your Databricks ecosystem. Traditional streaming, uh, we'll take a candid look at the anti-patterns step, and in point five, we'll look at the optimization techniques which we'll be discussing. Then we'll go through the use case overview, uh, and the solution architecture for that use case overview. And then we'll take you through the live demo, which is an end-to-end demo, and the lessons learned, and after that, Q&A. So going to step one. So we'll talk about the Lakehouse now. So Lakehouse is a single control plane that spans every analytics persona. So across the top, you see SQL workflow orchestration. You have real-time streaming. You've got ML and Gen AI, and all of them are running against the same tables, not 5 disconnected copies. So secure data governance is provided by Unity Catalog. Over here, you have governance gives you the ability to do role-based access control. Row, column, and attribute level permissions are all given through this secure data governance layer, which is Unity Catalog. So governance is enforced no matter which engine fires the query. The lakehouse is automatically governed through this Unity Catalog. Under that, the Delta Lake keeps the data in an open Parquet-based format, which is asset compliant again. Uh, and the lakehouse, as you know, is both a warehouse and basically a delta lake. So you can actually store unstructured data inside those delta tables as well. Uh, this delta lake allows for schema evolution and time travel. So you actually avoid vendor lock-in while still getting warehouse reliability. Finally, note the cloud logos at the bottom. Storage lives in your native S3, ADLS, or GCS bucket, while compute clusters scale independently. So there's the compute and storage uncoupling that the Lakehouse provides with you for you, and that's what we'll be going through: the compute and storage. How do we optimize each one? So here's how we cover the entire data to AI spectrum on Databricks. First, we have data engineering. So we ingest from every source, apply automated quality checks in this phase, and land everything in Delta. So analysts always see a single trusted table. This is the first part, which is data engineering. Then you come towards machine learning. And on that same data, we handle feature engineering, model selection, and hyperparameter tuning. And then the third one is Gen AI. Because the data already lives in the lakehouse, we can fine tune foundation models. We can build RAG pipelines without copying a byte because we're having the same data as ground truth. And we can also build, like I said, RAG pipelines without copying a byte. So prompts, vector indices, and guardrails, they all run natively on the Databricks platform. Finally, you've got MLOps. So we wrap the lifecycle with continuous integration and continuous deployment, automated testing, and Unity catalog-based model governance. So whatever model you publish in Databricks, Unity Catalog keeps a track of that, keeps a track of the lineage, keeps the track of the version, and you can store it there as well. The key message is that whichever column your business needs today, engineering, classical ML, Gen AI, or production ops, we deliver it on one unified platform, right? And this speeds up actually time to value and eliminates costly handoffs. So how do we think of this? Well, one way to think of it is if you guys watch Formula One, or if you're aware of like high complex and high power cars in Formula One. So Databricks actually gives us that Formula One car power. But every DBU that you use inside your Databricks workflow or Databricks notebooks or whatever, the DBU cost that is incurred by the cluster, think of it as premium fuel for that Formula One car. So there are two realities that matters a lot in Databricks, in your Databricks ecosystem. One's the power and the second is the complexity, right? So power comes at a price. If your cluster is running and if it's computing high complex queries, you're going to use some power, and there's going to be a power related to that, to the consumption of that query. And the more power a cluster requires to complete a query, the more DBUs are extracted, or the more DBUs are incurred, and those DBUs add up actually. And the second is the complexity drives waste. So usage now spans notebooks, autoloader streams, or DLT pipelines, SQL warehouse, or ML experiments, each with its own persona, each with its own spin-up script, and often often like we have no shared cost dashboard. So without a single governance layer and real-time visibility, ownership fragments, and the invoice balloons because we don't know who owns what pipeline. So we're just trying to create copies of that pipelines, and at the same time, what we're doing is we're having this layer of inefficiency we're building on top of the resource group inside Databricks. The main takeaway from this is that cost efficiency isn't a one-time tuning exercise. It's an operating discipline, right? You can think of it as that. And we'll show you exactly how the automated guardrails, autoscaling, photon acceleration, or delta optimizations can actually reduce that inefficiency and mitigate your DBU cost. So before we jump into the how, let's sanity check the what, right? We start every engagement with our client by answering 4 questions. Think of them as an MRI scan of your Databricks bill, right? The first question is, where are we overspending? So we pinpoint the top 5 jobs for our clients, which are basically the low-hanging fruit, which we can pick up and automatically or easily where we can recognize the inefficiency. And that would alone reduce half the invoice of the cost. The second one is, are we using compute efficiently? So we check median cluster utilization. Anything under 50% is instant savings, right? The third one is, what built-in levers are still off? What parameters are not being are just out there but are not being controlled, right? So photon, acceleration, autoscaling, delta life tables, optimize, right? If any of them are disabled, that's low-hanging fruit as well, right? Fourth, fourth is, how will we track savings tomorrow? So cost dashboards, budget alerts, and Unity catalog tags make optimization a continuous muscle, right? Not a one-time diet. So we have to keep these 4 questions in mind, and they'll guide the specific techniques we cover on next. So in this slide, we've got cost in streaming scenarios, right? If any of you who's working in a company and you have published a delta life table which is catering to a certain streaming workflow, point one is always on means always costing, right? If your streaming jobs are not stopping and they're on 24/7, you're incurring a bill that's going to multiply uh, uh, some folds if you do not control the when to stop. Number two is high frequency, high impact. So frequent micro batches, unnecessary writes, or over provisioned clusters multiply costs, right? So if you're running a script that is ingesting in micro batches, unnecessary micro batches, and there might be certain times in your pipeline where no data is getting ingested, and so these micro batches may turn out empty, right? You might not have any data that is landing inside your database, but the compute is running, which is inefficient. Number three is visibility and control are key. So if you're not uh, tracking your streaming workload through some dashboard, you're actually lacking in that area where you can actually see what's happening, how much cost is incurring per minute or per second. And cost directly impacts scaling. That's point four. So poor cost controls limits your ability to scale real-time use cases. That's pretty much self-evident. Uh, So we'll dive into the traditional streaming method first. In this webinar, we'll be mainly covering a streaming database, right? So we'll have to go through the traditional streaming method first to first let you know how streaming is widely applied by companies to manage their data pipelines. So here's the pattern we still see in far too many real-time pipelines. We've got fixed clusters, right? That's the top point. Fixed clusters, static resources. So teams size clusters for, let's say, Black Friday peak, and then they leave them running 24/7, right? So after the season ends, utilization drops to single digits, but the DBU dial never stops, right? Because you've got fixed clusters now. But with frequent micro batching without tuning, you can see that with frequent micro batching, you're actually that's triggering the pipeline for every 2 seconds, right? Whether one record or a million arrive. So you pay the same compute for an empty batch as for a full one. Plus, there's extra storage input-output cost. No data skipping or file optimization. So raw inserts actually create thousands of tiny delta files, and mostly with no z ordering or caching. So queries get slower, right? They're looking through each file to get to in order to execute the query accurately. So engineers throw larger clusters at this symptom instead of using z ordering or optimize or partition by or different or partition, even repartition. You can use multiple methods to actually data skip, but we don't. And regularly, what engineers do is that they throw large clusters at the same. They just may increase the cluster size, which compounds cost. Right? I mean, they will actually have a faster query running, but the cost of the compute will be increasing. And then there's lack of monitoring and governance. So without job level cost alerts, uh, a stalled stream can burn dollars for hours before anyone notices, right? So here's what a well-architected Databricks streaming pipeline looks like in practice. To the left, we have two independent event streams. You've got the fundamental data and you've got price data. And all of this is landing directly into a delta bronze tables, right? So because they hydrate continuously, each insert is asset compliant and it's instantly queryable because it's a delta-like table, right? So inside the box, we transform those feeds into notebooks or DLT pipelines, then merge them into a consolidated data table. So that the consolidated the consolidated delta table is that green table that you see in the middle of the first box, right? This layer actually applies a business tools, late arrival handling, and schema enforcement. So downstream customers always like see kind of like the clean and version data for you. From there on, I see that the delta table actually spans out to three workloads. There's the real-time analytics dashboard that may refresh in seconds. You've got the machine learning jobs that retrain on the freshest facts. And we can also do ad hoc exploration in the integrated workspace with the fresh data. So notice that there's one storage location, but many compute surfaces, right? Which keeps costs down and data governance simple. The key takeaway from this figure that I would take is like that by staging every stream in Delta first, we unlock asset guarantees, we unlock the other benefits of Delta tables like time travel or uh, scalable fan out without ever copying data or spawning separate clusters for each uh, sector in your company, like or audience. So let's kind of pull the curtain back on why the old streaming model bleeds money and reliability. There's always on compute, right? You've got fixed triggers in that. There's over provisioned clusters, and focusing more on the over provisioned clusters, I would say, because they're sized for Black Friday peaks, but run at 10% utilization the rest of the year, they're highly inefficient. So at scale, the micro batch model also introduced the micro batch model also introduces latency. So as your data grows, each batch spends more time shuffling and less time finishing because your data is growing, right? And recovery is fragile. So if a node dies, checkpoint-based restarts can replay huge backlogs, right? Huge, which doubles compute cost again. And finally, without intelligent scheduling or spend alerts, teams don't notice runaway jobs, right? They just simply don't notice any runaway jobs. So we have to keep these 6 pain points in mind. The optimization levers we cover next, the levers which we'll be pulling, uh, we will be reminding you how pulling those levers actually rids you of these pains. Right? So Here are the four levers. Uh, and one habit that consistently cuts Databricks spend by 30% or more is they're detailed out here. So number one, we have autoscaling and job clusters, autoscaling clusters and jobs. So this lets the platform add workers when throughput spikes and tears them down when the throughput reduces. And this is via auto termination. So when the stream goes quiet, it's going to lower the amount of compute that's provisioned. So that alone removes most idle DBU burn. Then you've got Photon engine, right? That's Databricks' own C++ vectorized engine. And what we've seen is that because this engine works fast on queries, it actually reduces the pipeline runtime. And we've measured alone about 2 to 3 times speedups with this feature alone. So fewer utilization of the compute means fewer minutes of compute burned and fewer DBUs. There's number three, delta life tables. So delta life tables, like we discussed, but what we'll be covering next is that they let you declare your pipeline, DLT orchestration, clusters, handles, retries, all of it. And then you've got delta lake optimizations, which you can do through Z ordering, auto compaction, caching, uh, what else? Partitioning, repartitioning, optimizing Z ordering. Yes, I mentioned those, and a couple more. And then you've got monitor usage and set alerts, right? Sorry, these are the five levers. Like I mentioned, the four levers, these are actually the five levers. So monitoring usage and set alerts, this is the most important one. And through this, you can tag every job with a cost center and surface the DBU cost on the dashboard. This dashboard, you can then have some alerts that can be triggered through this dashboard. So whenever cost spikes or when it hits a certain threshold, you can have emails that are generated and alerts that are generated to you, which you can then take action on, right? Autoscaling is actually, so autoscaling in Databricks, it's it's the easiest cost lever to switch on, right? But why does it matter? Well, daytime spikes, uh, or overnight lulls. If you lock a cluster at peak size, you're burning DBUs. The other 20 hours of the day, it's not even being used, let's say. The autoscaling grows for peak, then shrinks or shuts down entirely when the stream goes quiet. The key benefits are that simple policy eliminates that the simple autoscale policy eliminates idle compute, right? So what are the best practices? The best practices are to use autoscaling job clusters, not all-purpose clusters. So each pipeline has its own cost envelope because of this. And we always have to toggle auto termination. So let's say set it to 10 to 15 minutes based upon the use case so that forgotten clusters don't run all night. And then uh, for bursty streams that burst out data, we have to pair autoscaling with trigger available now, right? So data can only be then processed upon the available now trigger. So that way, the engine wakes up only when new data lands. So the bottom line is for the slide is like we have to flip autoscaling on, add guardrails, and when you remove the largest single source of idle DBU spend, uh, that's where your cost cutting uh, margin will lie. The Photon engine. So think of Photon as Databricks' turbocharged engine. It's a C++ built vectorized execution layer that replaces parts of the traditional Spark JVM path. But why it matters for streaming? Well, joins, aggregations, window functions, those are the heavy SQL bits. And the heaviest bits of any delta stream are written to use uh, are are rewritten. So the Photon, it takes your SQL logic that contains joins, aggregations, window functions, or recursive CTEs, let's say, and this engine rewrites them at the back end into SIMD instructions, right? And these instructions are cache-friendly memory layouts. And this basically reduces the time that is taken to complete the query. So faster queries the queries run actually faster with the Photon engine, but faster queries means two wins. One, your job's finished sooner, so you pay for fewer DBU minutes, and you can downshift to cluster size. Additionally, you pick up a Photon-enabled runtime or SQL warehouse, uh, you are instantly able to spin it up, right? So here's what turning on Photon acceleration actually buys you. Number one is faster processing, right? Queries that used to run in 40 minutes now finish in about 15 minutes. Lower resource usage, because each core does more work, you can shrink a 16 node stream to 10 nodes. Smarter scaling. So higher throughput per node means that autoscaler needs fewer workers to absorb a spike, right? The bar chart on the right is Databricks' TPC DS benchmark. So moving from a vanilla runtime to Photon shows up to like about 8 times speed up as you adopt newer DBR versions. So the best practices checklist is flip the Photon switch in your cluster or SQL warehouse config, pair it with autoloader plus Delta Lake, uh, and run an A/B test for a week. Track runtime and DBU deltas and publish the ROI. Nothing sells optimization like a before and after graph, man. That's what I've noticed. So let's jump into delta live tables now. So these are all components of the demo that I'm discussing with you. All of them will be covered in the demo itself. Delta live tables or DLT. Well, the DLTs is a Databricks declarative framework for building both streaming and batch pipelines. So instead of wiring up clusters, retries, and checkpoints by hand, you write simple SQL or Python that says that what the table should look like, uh, and you can do it through declarative framework. So DLT handles the how behind what tables are in and what tables are connected to what other tables. But why that's a game changer for streaming? Well, the service autoscales clusters. It retries on failures and enforces data quality checks, and these checks are called expectations. So if a record violates a schema or an SLA, DLT can quarantine it automatically, and no manual triage is involved. So there are no reruns. So here's how the Delta Live table drives cost down once it's in production. First, the autoscaling and recovery. Uh, First, give me a second, please. Okay. So the DLT benefits for cost efficient streaming. Once the autoscaling and recovery. So DLT allocates just enough workers to meet current throughput. The second is built-in optimizations. Features like auto compaction and optimize write, they actually merge tiny files as they're created, so you avoid the I/O tax that normally sneaks in months later. Third, you've got fewer failures and less waste, right? The best practices checklist for you is run streams in continuous mode for true low latency ETL, combine DLT with Photon, uh, autoloader, and Z ordering for maximum speed, and make expectations as strict as your SLA allows. So this is a very generalized way of me speaking. Uh, of course, the based upon the use case, we might hit some check marks on and hit some check marks off, but the ultimate goal will be to optimize the code and optimize the pipeline time, or and in turn optimize the cost associated. So additional storage optimizations. What do we want to communicate here? Well, even after you tamed compute, storage can quietly drain budgets and slow queries, right? So we have to input some sort of strategies. One's Z ordering, number two is auto compaction, there's delta caching, and some other strategies that we will be going through in the demo. So without a further ado, I would like to hand it over to Maz now, and we'll be walking you over through the demo.
Thank you, Heather, for that wonderful description and the overall content that you covered during the cost optimization. And hi everyone, my name is Moaz Ahmed and I am a data scientist at Royal Cyber. I've been working in close proximity with Databricks over the past few years and I've seen the platform grow and evolve into the kind of beast that it is. So today the case study is about a retail, and what we are going to do is that we are going to cover a comparative approach between the traditional streaming approach and the Delta Live tables. We aren't obviously going to run the entire streaming thing, but our main focus would be on the cost and how the optimizations are going to work. And basically, we'll show the techniques how used, and then the main part would be the cost monitoring dashboard. So over to the case study, we have the use case where we actually have the retail data, which contains different sorts of data, which contains different sorts of tables, files to it, and they are like interlinked through some keys. And what we are expecting is that once again we are going to see a comparison of how basically the traditional approach basically differs and what are the drawbacks to it as mentioned by Heather, and we are going to compare it with the delta light table to see the cost that we are actually going to infer. So now, if we talk about the business benefits, so the business benefits for this cover the scalability and performance at first, and then we proceed to the cost optimization. Obviously, with the delta light tables and Photon engine, the scale we are actually dealing with things that are highly valuable and high performing, and they are actually very, very scalable to a very high level. Then the cost optimization is obviously what the overall webinar is revolving around. And finally, efficiency and accuracy. We're going to see that the things are not just efficient, but they are accurate as well. A lot of manual tunings and a lot of manual handlings, they are created by Delta Light tables. So now, if we talk about the solution framework of the salient features of this, so we have the Photon engine, obviously that is the literally the engine behind the overall thing, and then the Delta Live tables that are the competitor for the traditional streaming tables, and then we have the database autoloader. Obviously, we cannot, the database on the streaming in Databricks cannot be described without an autoloader. Autoloader has become this principal part of the streaming, and combining it with Delta Live tables basically gives us a great head start. And obviously, we are going to see some sort of governance with Unity catalog as well, the how the schemas and with two different schema approach. And finally, what we'll be showing is a cost monitoring dashboard right there. So the cost monitoring dashboard will be the one that actually displays the end results of how the overall comparison goes. So we are actually very eager. I myself am very eager to display the results and show you the actual performance. And now the solution architecture. So we have a streaming data. Once again, the data might be batch streaming or the data might be a continuous stream depending upon your use case. We have like the streaming data that are the scheduled, and what we are going to do there, it is a part of the container and it will be ingested into our database environment in the form of Databricks notebooks and workflows. So now once we have the streaming data, what we are going to do is that we're going to implement a medallion architecture where we have a bronze layer, the ingestion layer, the silver layer, and the final aggregated layer to make, which will have some meaningful data. But the most important part, once again, is the cost monitoring dashboard. We are familiar with the process of a medallion architecture, right? But the cost is something that we are then interested in, and how we are going to see the cost. The database system tables. These are actually very powerful tables if one learns how to use them, because they are the ones handling all sorts of costing, relevance, pricing list, tier list, job data, everything is there in the database system tables. And we are going to explore the system tables and we are going to see how they can actually help us in understanding the cost processes that we are observing in our platform. So that was pretty much it for the solution architecture. And without further ado, let us proceed to the live demo. So I'll be changing my screen and you'll be seeing my Databricks workspace here now. Right. So this right here is now our Databricks workspace. And let us go through the workspace. So we have these folders first, the one related to our main agenda. And before moving, I'll just show you like a catalog. We have this catalog and how the catalog. So yeah, this cost dynamics, we have this Unity catalog schema, obviously that has restrictions to it. And we have this baseline tool table. We have these baseline tables and the optimized schema. So they are the two schemas that we'll be using to basically compare the results. And once we are done, so before moving to the workspace itself and showing you the notebooks, let me show you the data. So right here, this right here is the storage container in our Azure workspace. And as you can see, it contains this folder right here, streaming, that is actually connected to our notebooks. And within this streaming table, within the streaming folder, we are getting the schemas and we are getting the CSVs that are related to our retail dataset. So this right here, as it shows the address, customer address, and within those you would find CSV files that keeps updating at regular intervals. And similarly, we also have schema folder right here in it. Let me just go through it. So this right here is the schema folder, which basically continuously handles the schemas for the streaming files. And finally, we also have checkpoints that are relevant right now for our discussion. So if I go back to my Databricks workspace, right? So we move to this and we have these two optimization techniques and we have two implementation techniques and we'll see how they basically differ with each other. So first one right there is a thorough implementation and this the way it is structured right here, this through the bronze layer, we ingest the data into the bronze layer, then we have a silver aggregated layer and finally a gold standard layer. So this right here basically shows the overall procedure of how it is implemented. But let us have a deeper look at it and see where we are actually lacking while getting the streaming results. So now if we see, we are streaming the address data, right? And the address data, what we are using is that we are using spark.readstream. Okay, that makes sense. And we are using the autoloader itself. But so in general, this would seem like a very good implementation to a normal map. But what we are missing from here is how they are affecting the cost. So this infer schema, as you can see, the first and foremost, this infer schema is true. So what happens in this case is it is going to infer the schema every time the streaming is being called. So that is why if we have very huge amount of data sets and very large number of columns, it is always going to infer schema again and again before moving to the data extraction. Similarly, what we are missing right here is there is no optimization we could see. There are no triggers or there is no auto compact, auto optimize, there is no use of such. So this, if I run this just for a sample, we aren't going to run the entire thing, but this is what I was trying to explain. So as you can see, it has read the address data frame. That makes sense true. So let me just display address df. And yeah, so the stream is initialized and we can see that the address data will be displayed in a while. So right now, let's just give it some moment and see what basically the address data we get from the portal itself on the Azure. So so now the display query is updated, and as you can see, we have address data that is related to. We have address line 1, state, province, and so on and so forth. So these are the respective columns for the address. But we are not here to analyze the data. We are here to see what possible changes that could lead to cost reduction. So now let us move to how we are actually writing. So this looks on a higher view, this looks a good approach, right? So we are reading the string and then what we do is that we write the string in the format of a delta table. We have these checkpoint locations as well, and the checkpoints are there to basically infer the address over time. So, and we are actually appending it on an output mode. So that makes sense, right? But the important part right here this trigger is the most important, one of the most important thing right there in terms of writing the stream. So as you can see, if we do this and we don't handle the trigger, so what we are going to face then would be a bit serious. So let's say I remove this part, right? And I run this. So now what is happening is address data frame right here. It is like writing on it. But what we are observing is that it is not stopping at all. So that is why the trigger is very important. One of the most important things, specifically when we know that our streaming data is supposed to come for a certain amount of time and then it has to stop and then write to the database. So the trigger is there to basically handle these things. So that actually happened with one of our colleagues as well. So he did not apply this trigger there, and the job kept on running. So unless somebody or someone actually opens the notebook once again or manually goes through the notebook, he won't actually notice, and the trigger will continue to proceed. So the trigger right here is actually very important. So in terms of the trigger, right now we have it available now because obviously right now there's no streaming data coming currently, but the available now is the one that is handling things. Similarly, instead of available now, we have to basically we can manipulate this trigger. It can have a processing time of a certain time frame, like 1 minute or 30 seconds, and in that moment, only that moment, it would read the data and then it would like write the file. So that actually depends on the use case, how you know how your data is basically going to be entered. So this right here is a very important implementation, and we don't see any auto optimize, auto compact, nothing whatsoever. So these triggers, this is well, like one of the important parts out there if you need if you need optimization. Now proceeding towards the customer addresses. So we have this similar faults here. Inverse schema is available, it shouldn't be there at all, right? And then we are writing this to the customer address and then proceeding. So the good thing is that the triggers are like active, and you have handled trigger just to make sure that the streaming data once completed, that is being written into the files. So now if we could look at this, what they are doing is they're aggregating the silver tables, but you see that all of this is happening in the same notebook. So that is something that is not recommended at all. You should have a proper medallion architecture that should be implemented accordingly. And so just so in case if one of the you have like not only independence among the notebooks, but also you should know that if one notebook fails, you can basically easily debug that notebook and get exactly to that point. So what we are doing is that we are getting the customer table from here and we are making some aggregations on it. And we are proceeding with the aggregations to see basically a better silver level customer table and then the product table, and we are like applying the necessary castings to it, and finally we have this silver customers used once again, and we are basically creating the customers location level stats so that we get the overall location wise data and the demographics of the customer. So if we look at the gold layer here, yeah. So this right here is a gold layer that basically utilizes the two silver layers, and they are aggregated properly in the form of cross join. So we are getting the region distinction between them. So if we look at the results of the gold data frame, this right here shows the results. The country, we have the state, province, and the customer count, the product category for those customers, and the average pricing of that. And then we can use this in the dashboard. So this looks a simple implementation, right? But let's see what it actually is missing in terms of optimization. We have discussed it. Let's say if we were to optimize it, and let's see how the things would be different, right? So if we move back here and open the optimizer. So now, as you can see, this right here basically is the way an entire medallion architecture is supposed to be implemented. You have to have individual files and you have to have basically a proper foldering system right here so that the overall you can not only debug the issues but also you can refer back to any notebook you like. So now how DLT basically what are the techniques that we are currently using in this DLT, right? So as you can see, we have imported the DLT table. We have declared the DLT tables of the decorator. And now you can see the quality. We have set the quality to bronze. And that is why in the graph right here, you can see that these are in the bronze. And then auto optimize and auto compact. So we are getting the tables right. And we are applying the auto optimize right and auto compact just to make sure that the table definition is optimized in the most best possible way. So as you can see right here, and what we are then applying is that we are reading the stream. Once again, we are combining our delta write table with the autoloader here. And now, as you can see, there is no schema location. And once again, this cloud files. So this right here include existing files. That case is something that is something which I wanted to discuss. That you only allow this if you want to reread the existing files that are there. But if you know that the schema right here is and the schema, but if you know that the files that are upcoming, they won't be interacting at all with our existing files, so we don't have to read the existing files once again. So that is once again the optimization at the storage level or the delta lake level. And as we proceed from here, we see the schema evolution mode. So the schema evolution is like if for a certain scenario, like if for a certain scenario for us or for a certain reason we have a change in our schema, so what would we do then? We would use the schema evolution mode, and we can change this mode to basically evolve our schema if according to our desires. So we can force the schema evolution, or we can reject the schema evolution altogether. And this right here is that right here puts the throttle on the cost. We have the max bytes per trigger. So the maximum bytes per trigger right here, it basically allows the reading of the files in the partition way. So this what happens, right? It's more often than not we have the files that are huge or that are of huge sizes, and the partitions, if we do not properly partition them, or the maximum number of bytes per trigger, if we don't manage them, the reading of those files take ampers and ampers of time, and this can cause your streaming job to be stuck in an infinite loop. So this right here is absolutely necessary if you want to make sure that the call you are handling the cost efficiently. So now we have this bronze address rate, and similar to that, these were the optimization technique that were being used. Obviously, we're not going to run it on the runtime here. So this right here is the customer's data, the bronze customer address, and so on and so forth. So this right here is the overall look of how our delta tables operated. And now let's just see the jobs that basically comprise of these two. So if we look at the jobs right here, we have a baseline job run that is like the baseline run for the notebook that I shared, and then the optimized DLT pipeline. And this right here covers the DLT stuff. So what are other changes and other configurations that you could add? So like if you go to the settings in here, you see the name, production edition, and the mode. Right now it is triggered, and we have given the source, and finally number of workers, and we have enabled photon acceleration. Due to the photon acceleration, we can enhance performance by quite some while, as discussed before. So that right here, or you could set up the entire optimization pipeline through the JSON as well. So like if right now this is how the JSON of this pipeline looks like. So we have given the notebooks, and we have this addition schema, and we have the data sampling. Data sampling is you can, if like you want the data to be sampled properly, you can enable that as well. There are quite a lot of other configurations that you could add to this DLT pipeline, and this right here will is the demonstration of our current DLT pipeline. So the DLT graph, if we look at it, this graph looks something right here. So we have this overall medallion architecture that is being implemented, and finally, if we look at the gold standard data that we have in the cost dynamics, and we move to the optimized pipeline, and we just do this, and let me change to the serverless just for now. And this is the gold regional product insights, and This right here is the data once again that you can obtain. You can make any sort of visualizations on it, but the purpose was to see how and where you are supposed to make the necessary cost optimization techniques. So now this was the overall flow and the comparison. So how to basically analyze the cost, right? Now we are moving to the system tables. As discussed, system tables basically hold the power to help you get a command over literally everything there. So if we look at the system tables in here, we have the billing, we have the access, AI, billing, and so on and so forth. So if we look at the access specifically, you'll see that you have orders where literally everything related to the system tables and how the changes that are continuously being made at the development by the account to the workspace, all of these are being handled here. And but what would be the most interested for us is the usage. So now if we look at the usage, we can see the overall usage that has been implemented in here. So account ID, workspace ID, record ID, how this account was used, usage time, and everything related to the usage. And what we are interested is the metadata, right? So we can use this system table and the usage table as well to basically cover all the necessary. We can make certain combination of SQL queries to create to actually see which account, which user, which job ID actually costed us something, and that is what we actually did to find out the cost. And similarly, you have this lake flow. What I wanted to discuss this lake flow scheme as well. Now here we have the job task, the pipelines, the jobs, and the job runtime. So if we look at the pipelines, so yeah, so as you can see, this right here shows a bit overview of the pipelines and that we have run. Similarly, the job run timeline will show you all the details related to the job. So what we can do is we can use the content within these system tables, and what we can do is we can create we can see basically how which operation and at what time specifically which operation was impacting our results. So finally, when we move to the results here, so let me just go to the results. I'm sorry. Right, so after a comprehensive discussion about the system level tables that we have obtained, let us now proceed towards the keynote of this webinar and the results which we have obtained. So as you can see, we have the data monitoring dashboard that we are going to show you that shows a comparison between our traditional approach and the one which we have currently used. So if let me just go to our dashboards right here, and in here we see the monitoring dashboard. So this looks a bit more complex to understand. So let us just refresh it first and then add a few filters to it. So now let us refresh, and then what we are going to do is we are going to see the results for this workspace, the one where we are actually performing the webinar. And on the graph, you could see that the cost is on the y-axis and the duration is on x-axis for the consumption. So let it refresh, and now there you go. It looks a bit more presentable now. So let us add a few more date filters to see the more relevant results for the past few days. So let us go for the past 7 days and see the results, and I shall explain the graph and the cost that we are currently getting from. So this right here, I think it might need a bit more fine tuning. So what we could do is that we could add a daily filter to see how the results are being operated. So we have added the day filter right here, and let us see the results and wait for it. Yeah. So the cost right here, the current cost, the blue lines represent the interactive part, which is not relevant to us, while the red lines are the red bars, they represent the delta light tables, and the yellow lines represent the traditional streaming. So as you can see right now, even a general looks tells you that the delta live tables are actually outperforming. So here you can see the two are comparable, but then as we proceed to the next stage, the delta live tables were actually giving us better results. And here, as you can see, the tradition we added a few unoptimization techniques, And the traditional approach basically exploded there, and the delta lie tables, they were consistent. So this shows a remarkable difference between the two approaches if used correctly. So now, and for the next 2 days we had to like stop the delta live tables for due to some technical reasons, and now the recent we had a bit more volume of the data. So as you can see right here, even in this one, the delta live tables they are actually outperforming. So even though, as you could see, the results clearly show that if the delta live tables and the Photon engine they are implemented correctly, we could scale this to thousands and thousands of dollars of cost optimization. So yeah, that was it from the cost dashboard, and I hope you liked the overall demo. So now what we are going to do is that we're going to have a short look over the lessons that we have learned during this webinar. So let me proceed to that. Right. So now let us have a look at the final keynotes from this session. So, what were the actual lessons learned that we implemented during our cost optimization? So, if I had to categorize the entire thing, I could categorize into resource management, data optimization, and performance tuning. So, the resource management includes auto scaling and then choosing the number of workers efficiently and the configurations that you add actually to your data live tables. And the data optimization, these are the storage level optimizations which we handled. So these include the the Z ordering, the auto compact and auto optimized, and similar Delta Lake optimizations. And finally, the performance tuning, which obviously includes including the Photon engine accurately depend and the optimizing your query itself and the syntax and the type of syntax to use within either you're using Spark or PySpark or SQL query. So you have to be very careful about how you are actually ingesting the data. So these were the three major things that I would say are very the standing borders there that determine how your cost is going to be optimized. So that was pretty much it. And the final lesson, which I would say, is that instead of being scared of the cost and once a new technology or a technology that seems costly, it may not actually be. So the Photon engine, if used efficiently along with delta light tables, they can actually bring significant amount of reductions to your overall cost. So that was it from my side, and thank you all for attending this. I hope you enjoyed it the way I did presenting the webinar. And thank you so much once again. And I'd like to thank my colleague Heather, and you all. So
All right, thank you. But just on the closing bit, let me share my screen. We went through this, and then we went through the live demo. So, what's our offering? Um, where does Royal Cyber come in? Well, we do have our own Databricks optimization accelerator, right? At Royal Cyber, we work with clients to not just use Databricks, but to optimize it for real business outcomes as well. Whether it's performance tuning, cost efficiency, or uh, advanced preparing for advanced use cases, right? So our core offering here is the Databricks Optimization Accelerator, which is typically a 4 to 6 week engagement. We start by analyzing current workloads and costs, then optimize pipelines and clusters and then we introduce automations like CI/CD and governance with Unity Catalog, and finally we do the KT transfer, like the knowledge transfer, so your team is empowered to manage and scale. So think of us coming in and doing like a quick health check plus hands-on tuning. We're not just advising, but we're engineering side by side with your team. So uh, we go through 4 steps like I discussed: discover, optimize, automate, and enable. You can see them on the screen. Uh, Clients who've actually gone through this program with us have seen real impact. For example, one of our clients, that is a major manufacturer. has had a 38% boost in ETL pipeline performance and up to 30% cost reduction on compute usage. This is a sort of client that used to have millions of dollars as the Databricks cost, uh, right? Uh, I just want to know if my screen is still being shared. Yes, it is shared. Okay. So yes, one of our clients, we reduced their cost by up to 30%, right? We've also helped teams move from fragmented data access to a fully governed environment using Unity Catalog. And by this, we cut down on onboarding time and improving the audit readiness. You've got many features inside the Unity Catalog that gives you that power. Ultimately, what we do is that we help clients go from just running jobs on Databricks to running an optimized, governed, and cost-efficient platform, right? We make your ecosystem fully efficient end to end, right? So if you're already using Databricks, or if you're planning to use one, or if you're planning to scale your workloads, we invite you formally to explore with us. We offer a free Databricks health check to help quickly identify the low-hanging fruit or quick wins. And we also look and try to forecast the long-term improvements that we can schedule. And right now, I would like to welcome any Q&A on your behalf, whether it's related to the webinar, whether it's related to us as a company. Feel free to question us about that. I see Michael did ask a question during the webinar asking what computer language is this? Well, in the webinar, you would have seen a Python type language that's called PySpark, and it's optimized for running on Spark clusters. So, but it's closely related to Python. So, the language is PySpark. It has evolved from Scala. So, yes. Any other questions that we might have for now? Okay, I think we're good for now. We're not getting any questions. So I again would like to thank you all for coming in and joining this webinar. It was nice to host all of you. We'll have more webinars that will be coming up in our series. This is the first one, but thank you so much. Again, we do offer a free Databricks consulting to do a free health check. Uh, so you're very welcome to contact us whenever. Thank you so much.